Hello, I'm Angelina, and welcome back to another episode of our interviews. As always, feel free to open up the transcript or the description to better follow along and learn more about our guest speakers. Hi, I'm here with Simon, and if you don't mind, can I ask you a couple of questions?
Yeah, absolutely.
Okay, sounds good. So just to start off, do you mind sort of walking us through your journey through math and any key experiences you had along the way?
Yeah, sure. So I've always been extremely interested in math. I've never considered any career trajectory other than being a mathematician. So I've always known that that's what I wanted to do from the moment I knew that there were mathematicians in the world. Um, and I didn't know very much mathematics for a while. I was always very interested in it, but I didn't really have access to a lot of resources for a while. And until well, I started getting access to more resources in high school when I discovered competitions. I didn't know that they existed before then, so I didn't know what math counts was until I was too old to be eligible for it anymore, for example. So I never did it. And then in high school, I learned about them, and I was terrible. I basically couldn't do any problems. But I was inspired, and I thought that these were extremely interesting, much more interesting than anything else that I was seeing at the time. So I worked really hard for several years until I got to be able to do most of the problems. Um, and Also in high school, I went to SUMA, like I'm wearing the t-shirt, SUMA, and I learned a bit about algebraic topology, and that was really great. It was my first exposure to this kind of mathematics beyond the competition curriculum, and it was great. I wish I'd had more resources to learn about that kind of mathematics the rest of the time. So while I did a lot of competitions, I don't think that that was really what I was ultimately interested in. If I'd had better choices available to me, if I could have done the contest, or I could have focused more on learning abstract algebra and analysis and stuff like that, I would have tried to read books on these subjects. I didn't have anyone to help me, and I would get stuck and not know what to do. There were a lot fewer resources back then than there are now. So just being entirely by myself, trying to figure this out however I could. I did a little bit, but I wasn't really very successful at learning these subjects on my own. Whereas for the competitions, I had access to all the old problems and their solutions, and could just get on with it and read them all and solve as many problems as I could. And the ones I couldn't, I'd look up the solutions, and then I would learn how to do them. So it took a while to learn how to do all the competition problems, but it was a clear path that anyone can take. And so that was what I did. And that was my main job in high school, was learning how to win competitions, in particular, not doing my homework, which I very much stand behind. Uh, I got a lot more out of learning how to do competition problems and getting good at problem solving than I would have by doing dumb assignments that my teachers gave me. So this is ultimately a very good trade-off, and one that I highly recommend to others. Um, anyway, after that, I went to college. I went to UC Santa Barbara's College of Creative Studies, and the reason that I went there is the professor who was in charge of the program at the time used to write a competition every year to try to recruit people. And so I won his competition a few times, and so he invited me to visit and tell me, show me about the college, and I was really impressed with him and knew that he would take good care of me and make sure that I was challenged in learning a ton of math. And also, another thing about it, this college gives people a lot of flexibility. There are very few requirements. You don't have to take a lot of general education requirements. You can skip a lot of classes, not take the prerequisites. And if you try that and you fail, then that's your problem. But you have a chance. And if that works for you, great. If it doesn't work for you, then well, maybe you don't do that. But it's available if you want it. And that was really great for me. The summer before I started in college, I went to the orientation, and I met with the professor and asked which classes I should take. And he told me, yeah, you should take graduate algebra, graduate real analysis, graduate topology, first quarter of freshman year. Go. I was completely unprepared for these classes. but I've never had more fun with math than I did while failing these classes. Even though I didn't learn everything I was supposed to for the classes, I learned much more than I would have if I'd had to take all the prerequisites one by one until I got there. So I got as much as I could out of them, um, learned as much of the background as I could, at least given that I had no study skills and just wandered around mathematics aimlessly, reading whatever I felt like in any given moment. Um, but eventually I learned most of the things that I would have needed as prerequisites for these classes. And then by my second year, I was pretty much ready to take the graduate classes and do well in them. And then after that, I just took basically every class that was offered at the advanced graduate level for the rest of my college experience, the rest of my time in college. Um, yeah, so yeah, my job in college was just learn as much math as possible. I wasn't there for any to graduate school at Stanford. I did a PhD in math, in algebraic number theory. I think I did some interesting projects, but I wasn't always so happy there. Um, and well, so I mean, there are many reasons, but one reason is there's a problem with graduate school where you're expected to focus on your one area and spend all your time on the stuff that's related to your thesis. And it's easy to forget. All of mathematics is interesting. There's so much great stuff out there. Why am I just focusing on this one little area to get my PhD? But this is what you have to do in graduate school. And ultimately, it's what you're incentivized to do for the rest of your career as an academic. So the way that you convince someone to give you tenure is by becoming an expert on your one thing, basically. But that's not really my style. I remembered after I finished graduate school and had a little bit more flexibility that all the rest of mathematics is also interesting, and I wanted to think about that stuff too. So, so also at um, in parallel, while I was in graduate school, I started teaching at SUMAC. Because I'd gone there as a kid, and then I started teaching there because I was a graduate student at Stanford. It was very easy to start working there, and I found that to be more rewarding than anything else. I didn't expect that. I expected that I'd want to spend all my time on research and teaching would be kind of a drag. But then when I you know, some of my friends at Stanford told me that they taught at Sumac and had a great time, so okay, I'll give it a try. And especially since I went there as a kid and had very good memories of it. Um, and yeah, I just had an amazing time teaching um, and I also felt that it's very valuable to be working with these kids, giving them what they need. While I'm happy to try teaching math to anyone who is interested, the people I really understand are the people who have similar paths to me, the people who love math as kids and know that that's what they want to do with their lives. And that's where I find them. The ones who go to math camps, not maybe not age, that what they want to do is math and they want to focus on that as much as possible. And also while I was there, I remembered that it's the way we treat high school students is really terrible. You know, forcing them to do all sorts of stupid stuff instead of learning, just jumping through all sorts of hoops. I tried to push this out of my mind when I went to college and graduate school and focused on learning as much math. But then when I started teaching the high school students again, it all came back to me. And one thing that I realized very quickly is that it's a cruel joke that we play on these students to allow them to come to this camp for a month, learn abstract algebra or algebraic topology, and then the rest of the time they have to go to school and waste their time doing stupid stuff. Education should be something that happens year round, not just over the summer. And no one else seemed to care. So that meant that it was my responsibility to fix this. But starting new programs and organizing things is hard and scary. So I didn't want to do that for a while and just tried to follow the standard academic career path, you know, doing postdocs and stuff for a while. But then eventually I thought, okay, now it's time to get on with it and do what I actually care about. And create some program that's like sumac, but that happens year round. And so I started Euler Circle in 2015, and that's been my job ever since. And this is great. This is the best job I could possibly have. One thing that I think is very important in life is to find problems that I'm uniquely qualified to solve. Um, and if I were to become a university professor, the way that you get hired as a university professor is you convince some university that you're 2% than the next person they could have hired. So there are so many great people out there. You're not going to be that much better. Then means that the value you produce in the world is only 2% of what you do. Because if they hadn't hired you, they would have hired the next person who would have been almost as good. And you can maybe argue that, well, perhaps that other person would have got another job and would have been 2% better than the next person. Um, and this academic hiring process is nearly efficient enough to be able um, to take care of these kinds of things. So a lot of value is just lost. A lot of really great people don't get jobs because of inefficiencies in the hiring process, and it's just really bad. So the actual value produced to the professor is not very much compared to what you do. On the other hand, with my job at Euler Circle, teaching high school students, doing something that no one else is doing, I'm not 2% better than the next person. I'm infinitely better than the next person because no one else is doing this. I'm providing a genuinely new experience that no one else is offering. So that's something that's really important to me. If you can find something where you're uniquely qualified to work on this problem and to solve it, then you should do so rather than do something that other people could do just as well. And yeah, so another thing that's really great about Euler Circle, because I'm interested in so many different areas of math, not just my one little area, I'm well suited to teach classes in all sorts of different areas. So I don't know a lot of things at a very deep level, but I know a lot of things at a basic level well enough to teach a class on it. So I've taught classes on most of the undergraduate curriculum, plus various random topics uh, throughout math that wouldn't necessarily be taught very often in college. Students will enjoy as well. So this is a really great fit for me. So I think that should answer your question roughly, maybe.
Yes, it does. I also had like another question, sort of. I think you touched a little bit about on this sort of with like sumac as well as Euler Circle. Do you have any like other suggestions for like resources for students who are super interested in math and like want to get more into it?
Yeah, well, over the summer, there's a lot of programs that are available. There are lots of math camps. So Sumac is one, and then there's Promise, Ross, Math Camp, Mathly, Hampshire. Um, yeah, there's well. I hope I'm not offending um, all sorts of other people by not mentioning them who run these programs. But there are lots of these programs out there over the summer. Um, so there's no maybe not enough programs to cover all the demand for them, but there are lots of programs that are available. Whereas during the academic year, it's much harder, um, which is why it's so important to me to be running programs during the academic year when other people aren't. And I really wish people would. So other people, this is your chance.
Wait, if I'm not mistaken, I think your program also offers like mathematical research, right?
Yeah, sort of. Math research is essentially a gimmick at the high school level. People think it's shiny, and they basically shouldn't do it. They should just focus on learning as much as possible because doing research in high school before you've learned the basics is, trying to do these things with your hands tied behind your back. Why don't you learn the basics first so that when you get to research, you have a good tool set available to you to tackle these problems. Um, in, in my classes, the main way that I do this is that through the fall advanced classes at Euler Circle, I start a research group, and maybe those will turn into papers. Maybe they won't. I make no promises, but we'll try and see what happens. Sometimes they just fizzle out, and sometimes we actually get somewhere and write a paper.
Sort of on that note, are there any like cool topics or cool areas of research in math right now?
Well, there are tons of them. Um, so a few major results that were proven in the last not too long, um, tens was bounded gaps theorem. So this is a problem that goes back to the ancient Greeks. Are there infinitely many pairs of primes that differ by two? So, example, 29 and 31, these are two primes that differ by two. Does that happen infinitely often? And we still don't know the answer, but in around 2013 or so, um, a basically unknown mathematician named Yitang Zhang showed that infinitely many pairs of primes whose gaps are bounded. So he was able to show there are infinitely many pairs of primes. He wanted to get some finite number. Then there's been more recent progress that's brought that down to 246. So that's not two, but it's better than no finite number known. So this was a huge breakthrough um, in the 2010s. Um, yeah, there've been several more recreational advances. So one of them is some progress on the Hadwiger-Nelson theorem. The the Hadwiger points of using various different colors such that every 2 points that are distance one away from each other are colored differently. Then how many colors do you need? So it was known going back to probably the 1950s that you can't do it with three colors. You need at least four. There's a pretty simple argument to show that. And also, it's definitely possible to do it with seven. So the answer is somewhere between four and seven. And there was no progress on this for a while until something like 2018, when an amateur mathematician whose job is to try to cure aging um, uh, 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 tackle this problem can't be four. You must need at least five. So this was the first major breakthrough in this problem in about 60 years. So he came up with some quite complicated construction. He made some graph with over 1,000 vertices that shows that you cannot color all the points on the plane with only four colors, such that all pairs of points of distance one have different colors. So we still don't know the answer, but now we know that somewhere between five and seven rather than somewhere between four and seven. Four was eliminated. Um, Another interesting advance that I think was just last year is about aperiodic monotiles. Um, so an aperiodic monotile is some polygon that can be used to tile the plane without any gaps and or overlaps. But so with just that one piece, and you're allowed to translate it, you're allowed to rotate it, you're allowed to reflect it, but you just have to fill out the entire plane with one piece, and it can't be periodic. So so uh, so if you tile the plane with let's say squares, then you shift over by one square and you see exactly the same picture. So with this particular tiling, it's possible to tile the plane, but it is not possible to use this piece to tile the plane periodically. The only tilings using this piece are aperiodic. But people had wondered for a while, does there exist a single tile that can you can do it with that? So they'd known that you can tile the plane with several different tiles in such a way that all tilings with them are aperiodic. But it'd been an open problem for a long time whether you can do it with just a single tile. And it was discovered just last year, I think, that this is indeed possible. So these rather recreational problems, there are still great advances being made today.
Okay, thank you so much. Are there any like last advice or tips you want to share with the audience?
And have fun doing math.
Okay, thank you so much.